All right, let's do a few definitions, get them out of the way, and then we'll basically have a review. I think I just saw what it is I'm going to talk about. Review of Chemistry 2's half reactions, and we're going to make some cells so that we can find cell potential. Then there's an addition to what we did in Chemistry 2 called the Nernst equation, which we mentioned but never really did, that says you can set up something called a concentration cell, and when you change the concentration of the solutions in your cell, it changes the output voltage. Okay. And then, because we just said the word concentration, yes, our book doesn't deal the Nernst equation in terms of concentration, it does it in terms of activity. All right, let's get some generalities out of the way first then. Current. Current is the motion of electrons. It is the amount of electrons that flow through the wire. And we measure current in amperes. Now, mostly abbreviated to just amps. And 1 ampere, most of these electrical definitions are nice and uniform. 1 ampere is 1 coulomb per second. What does coulombs measure? Charge. So it's the charge of the electron traveling through the wire per second. Okay? Now, those electrons are moving from one place to another, and the rate of the motion of electrons is proportional to, use the little proportionality fish. No?
I've seen it, but I've never used it. We can start using it. Yeah, we can.
So you say that A equals B. All right? But if A equals B times C, then you can say A is proportional to B. So proportionality. And the other one that we have is
Okay, so what is that?
equivalent. Same as.
And can they keep using that? I was so confused.
It's equivalent. Yeah, so if we're saying joules per mole per Kelvin is equivalent to liter atmosphere, Pascal atmosphere, or whatever. Yeah. Where are the electrons going? What are they up to? What are they doing? They're involved in the oxidation reduction reaction. That they have left the thing that has been oxidized and they are traveling somewhere else to make something else be reduced. So if we can keep track of the electrons moving by current, we have a sense of the rate of the reaction. Okay. What's that say? Tin. From stannum. Tin, what group's tin in?
Not middle chunk.
Sure.
No. For sure is a transition. Close.
Group 4.
Yeah.
It's
Are we talking
here. Now, that line separates non-metals from metals, and tin is a full group away from being a non-metal. So it's a metal. No ifs, no ands, no buts. But germanium and antimony, there. Tin's definitely a metal. 4. 4. So it has an available 4 plus. Okay, but it's a stereotypical metal, which means it also has an available 2 plus. So over the course of time, this tin 4 turns into tin 2, and is that a typo? Who's written that down wrong? I've clearly written that down wrong, because that's the wrong way around, isn't it? Yeah. That's a plus, or I've got the 4. The 2 and the 4 are on the wrong side.
Okay. That's what I
Yeah. Where are we? 4. Yeah.
thought.
Yeah, yeah. Yeah. Can't have that and that be the same. Here's your tin 4. It's going to pick up 2 electrons and become tin 2. Is that an oxidation or a reduction?
Reduction.
It's a reduction. Your oxidation number is decreasing, and of course it's the gain of electrons. Okay. This occurs at 4.24 millimoles per hour.
Millimoles per hour.
So it will become 0.0042 moles. Moles per second. So we multiply that by, 2,000. And divide by, times that by 1/16. Because it's an hour.
For the coulombs though, would it be
Or
less
is
than, or would it just be 2 over?
Oh, okay.
What's the millimoles for? Are you supposed to do?
You need to convert that to the electrons and then also multiply that by avocado.
Like, why do we need to know particles if we're looking for
Do we? No, Faraday.
Wait, yeah, we had another equation before.
Well, we have Faraday's. So multiply by Faraday, not Avogadro. Sorry, that was wrong.
Oh, that
Faraday's.
equation from last week.
Multiply by Faraday's.
Try not to.
Yeah, multiply by 2 and multiply by Faraday.
Oh, I forgot there's a whole
And then
equation
divide
for
by
helium.
60 twice to get 2 seconds.
So would it be -2 since we lose 2, or is it just like absolute random?
And not just 60 to 60 seconds, and then 60 minutes. That make, oh yeah.
Yeah, because we haven't,
Cool, much per. Oh, and Faraday's number is a given. Got you.
I almost gave you a day there for the 24.
Yeah, next year's the day. That's unfortunate.
Oh, that would have been longer. So Dr. McGuire, would it be a 2 or a -2 for the I'm getting confused for the, I know you multiply by like the charge or whatever, or the, whatever that value, I don't know what you call it.
Yeah, you can do that, mate.
Okay.
Just 2 electrons, so it's 2.
Okay.
It's the event.
Oh, okay.
It's just the number of electrons involved in the event.
Okay.
And whether that's an oxidation or a reduction, feels like there should be a positive and a negative sign because they're moving different ways, but no,
Okay.
just for the event. As an hour passes, 4.42 millimoles of this disappears, turns into 4.24 millimoles of that. Okay, so a millimole, what's a millimole?
1,000 millimole.
So when 0.00424 moles of tin 4 plus turn to tin 2 plus. This is what we call a 2 electron. Did we decide whether this was an oxidation or a reduction? Just checking. This is a 2 electron reduction. So for every 0.0424 moles of tin, I get 0.00848 moles of electrons. Exchange hands, they move. Okay. One hour is 60 minutes, and 1 minute is 60 seconds. So 1 hour is 60 times 60 seconds. 6 times 6 is 30 seconds. So 1 hour is 3,600 seconds. This right here is a rate, something divided by time. It is millimoles of tin 4 consumed every hour, or millimoles of tin 2 plus produced every hour. It is a number divided by a time. That makes it a rate. Convert that to be 0.00848 moles of electrons moving every 3,600 seconds. Gives you the rate at which the electrons are moving. What's that number?
Didn't do it. Yep, 2.35 times 10 to the -6
we going to do with that number? Somebody answer.
Faraday's number.
Because
That's coulombs per mole. Yeah. Gives coulombs on top.
so the rate of electron flow is 2.35 times 10 to the negative 6 moles per second. I've already got it per second. What I have to do is find the value of Q. And remind me what Q was?
Charge.
Yeah. And how do I find it?
Let me find the coulombs.
What's that first value?
Number of
I know.
moles times the number of, we did the I charge times number of moles times the.
Mm-hmm.
Oh, yeah.
Okay. So we've kind of taken that into account because we've doubled. You can know it either way. The number of moles is twice as many electrons as there were tins, or you could say it's a 2-electron. Later on, we're just going to say this is a 2-electron event. Okay, so I need to throw Coulomb, Faraday's number in here at some point. Okay. A equals Q divided by S. I've already divided it by S. This is my 2.35 times 10 to the negative 6 moles per second. Keep your units in. It helps make sense of the logic of the math operation that you're about to do. And we're going to multiply that by Faraday's number, which is a
96,485.
big number, 96,485 coulombs per mole. And just like that, that mole and that per mole cancel each other out, and you have a number that is coulombs per second. Q is in coulombs, per seconds are in per seconds. Coulombs per second is amps. Don't know how many significant figures we had. There's 3 there. There's many there. So I'm guessing, yeah, 3. Because we had that 3. Okay. All right. I'm not sure how much more. I'm going to show some definitions. We've got 2 that are kind of allied together. It's something that we've been avoiding in chemistry, but one of us has aspirations to be an engineer. So we'll throw this in. And of course it is work. It's been very convenient for us in general chemistry that every time there is an exchange of heat, that we just say, heat. It all goes to heat. None of it goes to work. Nothing's been moved. You didn't blow the lid off the container. nothing that has mass has moved from point A to point B. Therefore, we will ignore work, but of course, you cannot. Potential. Potential is something that comes up. The higher you go into physical chemistry, we talk a lot about chemical potential, quite a bit. Here's another potential. Electric potential. Anybody know what that is before I write that up?
It's the voltage
It's
difference,
allied to that.
but it's not, it's kind of,
What voltage is potential difference.
I always get that messed up. Okay.
This is just potential.
But that is just, it's, equation. But it has to do with. Is that the I? No, that's
no,
current.
it's you.
Oh, it's new, actually.
Well, according to physics too, I took this semester, I don't know if it's.
Traction or repulsion between charges. Okay,
No, the U is
somebody needs to explain to Daniel how pollen gets attracted to
Yes.
Yes.
legs of bees.
So, a bee is positively charged, right?
Why is it positively
Because it
charged?
flaps its wings really, really fast. I forgot the number of the rate.
Can we have an appropriate demonstration?
And it flies over to the flower and takes out, and then because the bee is positively charged, the pollen, the flower is kind of neutral until it leaves, until the bee leaves, right?
I thought the flower was negatively charged.
Guy says it was negative.
Okay, I thought it meant
Now,
after.
why flapping of wings doesn't make you negatively charged, we never asked.
It's okay. But it flaps over to the flower and gets all the pollen stuck on it because it's positively charged, while the flower is negative and the positive and negatives attract.
And the pollen leaps off the flower and onto the bee. And then the bee moves to the next flower
And he wipes all out his
and
pockets.
pollinates the next flower.
Does that mean birds are positive charged? So they flap the wings?
No, I think it's static. It's static electricity.
I think it's because the bees are fuzzy.
It's fuzzy and rapid.
Yeah.
You can induce a charge with static electricity. And
It's like having your feet across the floor and getting all the charge on your shoes. Then you'd have someone in your leg.
and they have rules about which charge is which, and it's been far too long since I've
I learned it.
listened to anything about static electricity. Now, if we shine red light on the bees, does it dissipate their charge? Who won a Nobel Prize for that? Photoelectric effect.
Oh, darn it. Wait, Einstein.
Einstein did.
Okay.
There's a thing called photoelectric effect, that if you have something that is statically charged, shining a light on it doesn't do anything, but shining ultraviolet light on it dissipates the charge, the static charge, which makes no sense.
Is it because of the wavelength?
Yes.
Okay.
Yes.
Still makes sense.
Well, it means that the waves are interacting with the surface, not as waves, but as particles, by impacting the surface and knocking the charge off. Yeah. This is where duality comes from, that all waves, not just electrons, all waves have wave-particle duality, that we are living in a quantum world. On the macroscopic level, it's too big to see. Okay. We might even have that experiment in the physics lab. It's a brass plate in a bell jar with 2 pieces of gold leaf, and you just you take a cloth and you rub the top of the brass plate and you put some static electricity on it, and the gold leaf separates like this, and then you shine light on the brass plate. And when you shine light that contains ultraviolet, like you took it outside today in the bright light, the 2 gold leaves dissipate the charge. So in terms of electrochemistry, what we're really interested in is the potential difference. It's the gap. Potential difference is given symbol E, and it's measured in volts, and it represents the work performed when charges move position. What am I going to tell you? So work is, what do we measure work in? Oh yeah, like Newton meters.
I think it's Newton meters.
Yeah. Which is equivalent to. See, there's a whole bunch of equivalent. It's going to be joules. Although we could do joules per something else, but and it's going to be in volts, and that's in coulombs. 1 joule is 1 coulomb moving between a potential of 1 volt joule and coulomb. These are all people.
Yeah.
1 joule is equivalent to 1 coulomb moving through 1 volt of potential difference. Okay, here's a question. If 2.4 millimoles of electrons travel through a potential difference 0.27 volts, how much work is performed? Work is mass times distance, right? You have to physically move an object from one position to another. Electrons have mass and they move from place to place. So how much work are they doing?
So we just have to calculate the charge.
You need a Q and then you need a W. W is EQ. And we don't know what Q is just yet.
Isn't that times change it to volts and then times that by
Yeah.
1.6?
Now, sorry, I was talking.
You're good.
I had a read of our book to see when is it going to stop using this particular form of the equation, and it doesn't. Q equals N, N, F, right? Later on, when we turn that into the, you'll see it. I don't want to get ahead of myself, but there's a form of this that we've seen before, and they keep these two together. You'll see it when you see it. I'll show because it's coming next. I think that the simplest thing to do is to pull this over here and say charge per mole. But it's not what our book wants. It wants the total amount. Okay, 2.4 millimoles. What's a millimole?
1,000.
So which N is which?
Oh, the big N is the
So N is the number of charges. What's the charge of an electron? 1. It's 1 minus. So this is a 1. We didn't specifically do that the last time, but do it in your head, right? And then N, the big N, which is never the big N in chemistry, it's always the little n, is number of moles, which is 2.4 millimoles, with the conversion factor of 1 mole is 1,000 millimoles. Multiplied by Faraday's number, which we should be able to remember at this point. 485. All right, coulombs per mole. Those millimoles cancel, and then those moles cancel, which gives us a number in coulombs. Have you seen Mr. Coulomb, Dr. Coulomb?
Dr. Coulomb. That sounds.
Pull him up. What's that? Volta was real, Coulomb was real, Joule was real.
Do you have the first name?
Can't find it. Henri? Isn't his first name Henri? H-E-N-R-I?
This guy?
Yeah.
Did he win a Nobel Prize?
We need a number here.
He got 231.
Who?
231?
Oh, okay, that'll do.
His name isn't Charles or Augustine.
Oh, okay. All right, you have Q. Now that you have Q, you can do W equals E Q. What's E? Volts multiplied by 231 coulombs. Coulomb is equivalent, look, I used it, to a joule.
I got 62.5 or 63 for.
How many? We only have two significant figures, so 63. Okay. All right. Here's where it might start getting familiar. I'm going to run through all these definitions first. Oh, am I going to do this now, or am I going to do power? Let's do this one first. Free energy. Free energy represents the maximum possible electrical work that the reaction can do. Okay, so I've been trying to talk with my Chemistry 1 students about this. When a reaction does what it does, let's talk about, say, maybe thermodynamics, endothermic, exothermic. Okay, the reaction proceeds, and there is heat exchanged. With whom?
The surroundings.
The surroundings. So, when the reaction is going to do something, it has to do it to what's available. It's going to perform it on its surroundings. So this maximum possible electrical work that a reaction can perform on its surroundings. Okay. How much work could this thing do? This one that you just calculated. How much work could it do? It could do 63 joules. So what's the maximum that it could have done? 63. Okay. What's the maximum that it could have done to its environment? If we take this back to heat, when an exothermic reaction exchanges heat with its surroundings, the heat leaves the reaction, goes to the surroundings. When we talk about what's happened to the surroundings versus what happened to the reactions, they're the opposite of one another. One gives its heat away, and one accepts.
Oh, okay.
What's our symbol for free energy?
Oh, sorry.
We always talk, you can do G on its own, but delta G is where the money's at. It's happening to the surroundings. It's the opposite. Work is done on the surroundings by the reaction. So it's the opposite. Okay. negative EQ. Now, we've seen delta G before. Tell me everything you remember about delta G.
It is related to entropy,
Ah.
and temperature.
Yes, it is.
Delta H minus delta TS.
That's the big one. That's the first one that we learned.
There's also equivalent to something with Faraday's,
Mm,
right?
mhm.
An E something or another. I
Mm.
forgot what the first thing was. Was it
Mhm.
QEF? No, it was not.
Mm.
It was some NEF. Negative
Yeah.
NEF.
How many N's?
Oh.
Just one of
Just
them.
a little one though.
Yeah.
It's the little. What the
I
heck?
know.
What the heck?
I know. And our book
I'm so bad.
still refuses to take the other N out of the calculation.
Why won't they do it?
Delta G equals delta H minus T delta S. And if we remember back, this number is big.
Big.
Enthalpies are in kilojoules. They're usually in kilojoules.
Yeah.
Note I didn't say kilojoules per mole.
Say it again?
I did not say kilojoules per mole.
Okay.
Because for delta G is going to be measuring for a reaction. And delta H is for a reaction.
Yes.
And for a reaction, we don't say delta, we don't say kilojoules per mole. Because kilojoules per mole of what? If my reaction is N2 plus 3H2 makes 2NH3, and I find out that this is not really the value, but that's 1,000 kilojoules. If I say it's kilojoules per mole, it can't mean that and that at the same time.
Yes.
That's true, but in Hess's law, I feel like I remembered it being kilojoules when we were doing the reaction.
When it comes to a reaction, you drop the definition. Now, if I wanted to say per nitrogen, because there's only one of them, I could say kilojoules per mole and relate it only to that thing. But then this number would change and that number would change. But the reaction itself, as written, gives me this heat. Yeah. So those are usually big in the value of kilojoules, and entropies are small. They're joules. And then this is the deciding factor, because temperature is usually in Kelvin, it's usually in hundreds. And these hundreds of joules might be enough to impact these thousands of joules. Because if this is 10 joules, then 100 times that now makes 1,000.
Yeah.
Okay? So this tilts the balance. For a reaction to be spontaneous, this delta G equals delta H minus T delta S tells us a reaction is thermodynamically spontaneous when delta G is negative. And that makes sense. Because delta G gets to be negative if this term is negative.
Yeah.
If that term is negative, then that means your reaction is exothermic. It's giving out heat. If it's giving out heat, it means that the reactants are lower in energy than the products are lower in energy than the reactants are. That sounds like a winner, right? And then it also means, because I've got a negative sign here, that entropy could be a positive value. And if the disorder in your reaction increases, It increases the entropy of the universe. And anything that increases the entropy of the universe gets a thumbs up from the universe, because that's what the universe seems to want. Okay.
Oh, right.
Delta G is linked to the equilibrium constant. And delta G is related to potential difference. Faraday's constant, cell potential. We haven't seen a cell yet to do the potential of the cell, but it's coming. All right. Delta G equals n negative NFE. Comes from here. Delta G is negative N F, that's this term, E.
And then we just drop that big N because.
This is usually written as delta G equals NFE, meaning delta G here, but this is kilojoules per mole.
That's where the big E comes. Oh, sorry. It just came.
This is how our book has it. Delta G equals negative NNFE. That is not what we learned in general chemistry. Okay, one more. Power is volts times amps. What do we measure power in?
No, it's not a chemical concept, but it's right there in the book. So I figured I'd include it.
What's the physics definition? Like the electrical physics definition? I was wondering about that.
And I'm like, watts.
Oh.
Also a person.
All these people.
James Watt. James Watt allegedly watched the kettle on the stove or on the fire coming to a boil, Scottish guy, and noticed that the lid rattles when the water boils, that there is potential inside the boiling water to move a physical object. Now, don't dwell on the fact that Aristotle wrote about this 2,500 years before Watt did this, but Watt actually said, all right, I'm going to build a device. I'm going to build a device that will have the steam moving. And he invented a steam piston, which gave us the locomotive train, and then gave us steamships, which in turn gave us the British Empire.
Oh, you did tell me.
We had the best ships. We were 50 years ahead of everybody else, because James Watt gave us steam trains and steamships.
So who was the other guy you said was from France?
Carnot.
What was he doing?
Carnot actually figured all of the thermodynamic, why heat moves from place to place, entropy.
Was it the heat engine or the heat?
Mhm. Yeah, so in chemistry and in physics and in engineering, there are Carnot engines about how heat moves from place to place within the physical device. And there are simplified ones, and then there are like 4-stage Carnot engines. Yeah, he actually wrote it all down. Okay, let's go back and look at redox. Chemistry. What's oxidation?
The loss of electrons.
And we usually see that demonstrated by which side of the periodic table?
That is the right side, the non-metals.
Oxidation metals.
Loss of electrons. Oh, no, that's metals, sorry. It's on the left, that there's a loss.
Oh, that's a good way to do it.
If you lose electrons, you become positive. That is a trait of the
Left-hand side of the periodic table. And that reduction is the gain of electrons, which is characteristic of the right-hand side, the non-metal part of the periodic table. And just the way that we have mass balance and energy balance, there needs to be electron balance. That the amount of electrons lost must be the amount of electrons gained. Okay? So you cannot just make this stuff up. They have to balance. Let's do one and break it down. Here's a reaction that has been known for a very long time. That if you take a metal and you add acid to it, what happens? We should do this.
We should, can we?
We can do it on Thursday.
Wait, were you talking about steel and nitric acid or something like that? I forgot.
I know you mentioned like, oh, it's in the back, way back when.
And I want to use nitric acid. You don't remember that?
You were like, oh, back in college, and then you
You were
were like, your lab
your
books
lab
and
books.
stuff. For other labs we could do.
Oh,
Yeah.
okay.
And
I have a couple
I
of
think you
ideas.
said that we couldn't do it because we don't have steel on hand or something like that.
We couldn't do it because what?
We didn't have steel.
Oh, manganese in steel, yeah, I haven't discovered that
But
we have it yet.
pennies. We had that one
It just isn't illegal to destroy federal property.
but it dissolved it, so would it?
What happens when you add metal to an acid? You make a salt. Plus
No.
hydrogen gas.
Oh, was that is that what was?
It bubbles. So you can take some magnesium, put it in with hydrochloric acid, it will bubble. You put your thumb over the top of the test tube and you hold it until you can't hold the pressure in anymore. And then we light a match, and hydrogen's explosive.
We did that. We did that with Caleb. I have a video recording. It didn't go as long as we wanted to, but she did do it.
And the hydrogen should be explosive enough to blow the match out. All right. Let's go. Magnesium as a solid plus hydrochloric acid in solution goes ahead and makes magnesium chloride and hydrogen gas. Balance it. Because we need a balanced equation. And then, never satisfied with having a balanced equation, we need a complete ionic equation. And then the complete ionic equation will give us the net ionic equation. This should all be familiar to you, which will tell us what's actually going on. What group's magnesium in?
2+.
Magnesium is in group 2, therefore it has a fixed oxidation state. And the chlorine from hydrochloric acid is in which group?
7.
Which means it has a fixed oxidation state of -1.
Yes.
Stuff in the middle has a variable oxidation states, but things at the edges have fixed oxidation states. So what's the chemical formula for the salt?
MgCl2+.
My magnesium chloride is MgCl2. And is it soluble?
Chlorides are solid.
Most chlorides are soluble, except for cadmium, mercury, lead, silver. So,
This is solid.
soluble. And then we're going to make hydrogen as a gas, like that.
H2.
Yeah. Hydrogen, group 1, has 1 valence electron. That's radical. It's a pair of electrons. It's never going to exist as an individual atom. Not under the conditions that we know. Okay, is that balanced?
No.
No.
Gas needs to be doubled.
1 magnesium, 1 magnesium, 1 hydrogen, 2 hydrogens, 1 chlorine, 2 chlorines. Now it's balanced. Okay, solid, aqueous, aqueous, gas. In the complete ionic equation, you take anything that's an ionic material that is dissolved in water and you ionize it. And you let it be the electrolytes. So my 2 equivalents of hydrochloric acid don't exist. It's 2 equivalents of H plus and 2 equivalents of Cl minus. And because the magnesium chloride is soluble, that also does not exist in solution. And it gives you this. That's the complete ionic equation. And then you take out your red pen, and anything that's a spectator ion goes away. How do we know if it's a spectator ion?
There's
one on both sides, well, there's two here and two there,
The
so
same-
I
one
can't
of the
cancel
same
them then.
date.
Is only one magnesium. Those two hydrogens, this magnesium 2 plus, that hydrogen. Okay, so the net ionic equation is some magnesium reacts with some protons and makes magnesium 2 plus ions and hydrogen gas. What? I'll let you write. You there? What is the oxidation state of the magnesium metal?
0.
Things that are in their naturally occurring state have oxidation states of 0. And magnesium's naturally occurring state is a magnesium solid, it's metal. And that's a +1, and that's a +2, and this is a
0.
This is also a 0. Okay. First up. What's on the board is being oxidized?
Magnesium.
From here to here, I go from 0 to 2 plus. Every time my oxidation number goes up, that's an oxidation. This, therefore, is a 2 electron oxidation. What got reduced? But this goes from +1 to 0. That's only a 1 electron reduction,
But it's happening twice.
but there's 2 of them. So this is 2 times a 1 electron reduction, which means I have 2 electrons changing hands. Okay? They have to be equal and they have to be opposite. Good. All right, we'll call it a day. Next up, we're going to put 2 reactions in the same container, or at least partitioned container. And we're going to have this oxidation and reduction. So if this happened in the same container, we could still harvest that energy. But if we have them be separated from each other, then we can make the electrons flow through wires between the 2 reactions. And we're going to take a reaction that something is oxidized and something is reduced and split it into 2 halves. And we're going to have a half reaction and a half reaction that are actually physically separated from each other, but still do the work of a redox reaction.
Yeah, it is.